Okay, Assalamualaikum and good morning. So today we continue with lectures. We only had less than an hour actually, from last week, and then we had a public holiday on Thursday. So we are actually behind time. So let me try to go through what we did from last week. So let me share. Hopefully there's no problem today. Okay. Okay, you should be seeing my screen now. Can someone confirm this? Okay, great. So let me go to we look back at what we have done last week. We did not quite finish it, but no. So let me just go through a little bit what we did. So we had defined entropy and all these Carnot cycles, and then again I have not uploaded this, so I will do this after the lecture, inshallah. And then we did how to measure entropy. So for the case of ideal gas or perfect gas, this can be done easily. And then we talked about possibility of latent heats. Okay, so this occurs when let me just use my pen here. So the place where you have latent heat is when you have processes, okay, where there are phase changes. So in other words, heat is put into the system without changing the temperature of the system. So we need to include those, and essentially that will actually complete how we measure entropy in the end. Okay, so we talk about Troughton's rule. Okay, that's better. Air conditioning is too noisy. So and then we write down this process going from a solid melts into liquid, and then the liquid vaporizes, and essentially we can calculate those provided that we know what is this function of heat capacity at constant pressure. Okay, so then we talk about possibility of defining entropy at absolute zero. That is going to be a problem, but essentially one can do this by some form of extrapolation. Okay, the example that was given in the book, I'm not sure whether I've gone through this, but it's in the notes later on, which I will upload. So the example is given for solids below 10 Kelvin. So the heat capacity is actually given by that, and then one could actually write down the equation for the entropy in this particular case. This can be determined easily. Okay, the only problem is actually this. Okay, so the other one is essentially what is this parameter here. So in other words, one needs to do probably a data fitting kind of thing to determine what your constant of proportionality here. Okay, so in this particular case, the example given in the book is looking at gold at temperature of 10 Kelvin, and the heat capacity is actually given by that, and essentially we can determine the constant of proportionality multiplying t cubed here. Okay, so again, in the end, that all of that does not determine this entropy at the absolute zero temperature. Okay, so one could try to do again as you sort of plot your what you call entropy with respect to temperature. Then one can try to extrapolate this and then try to determine what S naught is. Okay, but here even extrapolation, one could not rely on that, because there will always be some new sources of entropy that is not really readily known above a certain temperature. And today we know that this occurs, there are a lot of different phases of matter at lower temperatures. For example, an insulator, for example, can go to, for high TC superconductor, for example, you can go from an insulator to a high TC superconductor. Okay, so there are phases which are quite unknown to most of until today. People are still discovering new things. Right, and also the other example given in the book is essentially the metal. Okay, so at high temperatures, you probably have that T cube dependence, but at low temperatures, one can actually see this dependence on just the linear power, just T, and at low temperatures, this contributes more than T cube. Imagine T is going to be very small. Okay, so T cube is going to be much smaller at lower temperatures. So in other words, this will dominate more than T cube, as an example. So all of these are required to do extrapolation to determine what the value of S naught. Okay, but again, there are no surprises always been, when you do low temperature physics, there are always new surprises. There's a theory that says, okay, what can be done essentially is to talk about entropy change. Okay, so if there is any entropy change with respect to the transformation between phases, that entropy change will approach to zero as the temperature goes down to absolute zero. Okay. The other one example given in the book is essentially the two forms of sulfur. The orthorhombic form is the common one, probably stable almost in all temperatures, but the monoclinic one is stable between this temperature. Okay, and then essentially there will be phase transition between these two forms. So one could actually try to calculate what are the changes in entropy over here. So in this case, the enthalpy change going from orthorhombic form to monoclinic form can be determined here or measured to be given that, and then you can actually calculate your delta S, which is a change in entropy between one phase of the sulfur to another phase. And at the transition temperature also, one could actually determine the entropy experimentally, and one finds this to be equals to according to these equations. Okay, and you can see the difference between the two forms is not that big, between an additional 37 joule per Kelvin per mole to another one which is 38 joule per Kelvin per mole. So the difference is quite small. So one expects if we go down to absolute zero, then the differences between the two will adjust, the changes of entropy between the two will be just 0 as well. So that gives us a third law of thermodynamics. Okay, this is a very complicated way of what you call stating it, but this is actually equivalent to what Nernst was actually mentioning. I think the one that I've learned is actually the form of Nernst, but here is just saying that if you have entropy of each phase, for example, which tells us that okay, you can have that stable state, meaning each phase is it will be stable at some point, okay, and that is taken to be 0 at absolute temperature, absolute 0. Then whatever phases the substance is in, then you expect that okay, the entropy is going to be 0 at the absolute 0. Okay, so the other picture that one also has for this third law of thermodynamics is that entropy is 0 for perfect ordered states. Okay, and of course this is not really possible to determine experimentally, but the point is if you have perfect order, entropy in some interpretation can be interpreted as disorder. So when you have a perfect order states, then your disorder is going to be 0. So that's essentially it fits the description. But then of course you also think about okay, maybe there are other types of material that is not quite inside this idea of perfect ordered states. Even as you cool down to absolute 0, it still maintain a certain form of disorder. Okay, things like your glass is definitely one of them. Okay, so this is excluded from this kind of statement of the third law of thermodynamics. Okay? The other thing is phrased rather differently in this particular book is that okay, your entropy is also proportional to the amount of material here. So here is the number of particles in the system. So as you increase the number of particles, then of course the entropy can also be bigger in that sense. Okay, and this is in some books saying that entropy is an extensive quantity. Okay, so I think that was probably the thing that we did, and then we go into free energies. And I think I've introduced Hemos free energy. We have this as a first law. Remember, this comes from dq reversible thing. Okay, so and then you have your T, or actually the inverse temperature being the integrating factor of your heat here, and then you can rewrite the first law to be given in terms of that. Okay, and one could rewrite this as that, and then you see there's a z differential here, a z differential here, and you can combine these two to get this quantity, which defines a new actually it's a state function in this particular case. State function, just like your internal energy is a state function. Okay, so here is another state function which is called Hemos free energy. Okay, and one can use this to look at changes into the system. So if one looks at this, for example, one can rewrite. Is there somebody coming in? I think it's auto admit. Okay. So if one makes a small change in this Hemos free energy, then one could actually rewrite it in terms of this. Okay, your du, it can be re-expressed here, and then what happens is that your TDS here gets cancelled off, and you are able to rewrite your small change in f in terms of a small change in t as your state variable and small change in v. So in other words, I can now think of, okay, I can think of your Hemos free energy to be given by a function of temperature and volume, and then a small change of f is now given in terms of your partial derivatives. Okay, there was some mistakes. This is dv. Okay, so I have a small change in f written in terms of small change in t and small change in v, and then looking above with this equation, okay, these two equations here, and then you'll be able to equate that, okay, your entropy is now can be written in terms of partial derivative of the Hemos free energy with respect to temperature, and your pressure in terms of free energy, different partial derivative of free energy with respect to the volume. Okay. Once you do this, for example, sorry, not feeling well today. Once you do this, if one thinks of your state function f here being having all the nice properties of analytic function or smooth function, okay, then one should be able to define second order derivatives in this way. Here are the second order derivatives with mixed variables here, okay, t and v, and then from calculus we know that this does not matter which one comes first, so this should be equal, and then we have essentially this relationship between the differential of entropy with respect to volume with the differential of the derivative, partial derivative of entropy with respect to volume to be equal to the partial derivative of pressure with respect to temperature. And this is known as Maxwell relations. There are 4 of them because there are 4 different state functions that we can actually look at. We shall see in a minute. One of the good things about Maxwell relations, you are able to, if you look at this, later on you see that your S, P, V, and T are essentially state variables. Then one of the things that one can actually do, just vary the state variables and see how it changes, and you have this relationship between the state variables. Okay, so these are important things that one can actually do this and then employ this or use it in an experiment to determine things. Okay. The other thing that we have actually done, so we have done a Hemos free energy, but we also see the technique that one uses in this Hemos free energy is the one that we have also seen in enthalpy. Remember, enthalpy is just taking this this differential of U plus PV. Okay, so essentially one uses the internal energy together with your work done, for example, to define enthalpy. Okay, and then we are able to show in this particular case, if you do that, this is just re-deriving the previous equations, and then you are able to write your enthalpy change in terms of the differential of your entropy and your pressure. So in other words, I can now write your enthalpy as a function of the state variables of entropy and pressure. Okay. So in this particular case, one can actually identify this now. So this would be, say, partial derivative of your H with respect to S, ds, and this would be partial derivative of H with respect to P dP. So in other words, we identify this to be your T here and this to be your V here. Okay. So again, these are the first order derivatives. Okay. So again, if you assume certain good properties about the state functions, then we should be getting another Maxwell relations, which is essentially this. Okay, so you look at this, for example, this is actually partial H, partial S. So you take partial T, partial P, okay, like this, you get a second order derivative of the mixed type, where you have at the denominator to be partial P, partial S. And then over here, you can also do partial P, partial S. Okay, or partial S, partial P. So then you get another Maxwell relations. Okay. And yeah, I mean, again, you can see that these are all state variables that one can actually manipulate in experiments if you want, and then one is able to establish certain properties of the system. Okay. Finally, there's one last free energy that we want to define, which is we're going to look at the whole thing now. You have this internal energy, and the one that temperature with the entropy, and then pressure with V. This like your mechanical work here. So and you combine this in this particular way, okay, and you take the differential of this, and then you'll find that okay, some of this will cancel out in the end, and you're left with an expression which multiplies a differential in T and a differential in P. Okay, so one defines the thing that you have over here as what we call Gibbs free energy. Gibbs is another one of the pioneers of statistical mechanics. Okay, so here we have another state function which tells us, okay, this is change in T, this is change in P. So in other words, your Gibbs free energy can be thought of as a function of temperature and pressure, okay, which is convenient because those two are the normal ones that we vary inside experiments. Okay, and essentially we get this so-called Gibbs free energy, and then again, if you do the first order derivative, then this would be what? This would be dg dt, and this would be dg dp. And there you go, you get identification of your S with dg dt here, and then your V with dg dp. Okay, so this is the first order derivative, and then you do the second order derivative with a mixed variable thing. So if you have T here, then I want to do another partial derivative with respect to P, then I will be able to get that partial S, partial P, constant temperature T, and then relate with this here partial P, so I need a partial S, sorry, partial T. Remember that G is a function of T and P. So here I will do another partial derivative with respect to T, and I will get that. Okay, so again here is another relationship that sort of relates different state variables. Okay, and finally, of course, we have the internal energy itself, which we have done this previously. So U is now defined as a, well, okay, I'm rewriting your first law in terms of TDS here. Previously it was dq here. Okay, so now I'll be able to write it in terms of TDS. So here is a change in S, change in V. So I can write your internal energy as a function of entropy and volume. Again, thinking in terms of first order derivative here, first order derivative here, I'll be able to identify your temperature as partial U, partial S, and pressure as partial U, partial V with a negative sign. Okay. And from there, that's the first order derivative. You can also do the second order derivative, then you get another Maxwell relation, which is given here. So there are 4 Maxwell relations. You do not need to memorize them, but I'm expecting you to understand how this is actually derived. So where does the thing comes from? It comes from 4 state functions. One is your internal energy, the other one is what your Hemos free energy, and then your enthalpy, and finally your Gibbs free energy. Okay, so you get all this from these 4 state functions. And that should complete the lecture from last week. Okay, so we are a bit behind time, but the other reason we are behind time, I don't have ready notes for this. For the next part of the lecture, I'll be writing on the whiteboard because I don't have it typed yet. So let me go to the next lecture here. Any questions at this point? I should be giving you at least an assignment before your first test. So I'm not sure when precisely in the first test. I'm pretty sure you have many tests on the 5th week, right? So I might postpone this to the 6th week because I have another subject having a test on 5th week. Okay. So, but be prepared to have your test on the 6th week. Okay. Any questions? Okay, good. So now I'll go to the whiteboard. Probably most of you learn about second law as the law that entropy never decreases or entropy always increases. So how does this relate to the ones that we have learned so far is to be able to use some of the things that we constructed a few things already in the past 2 lectures or so. So one of them is essentially your Carnot engine. Set write this properly. Hopefully you can you see the whiteboard, right? Okay. I hope my handwriting is what you call good enough. Okay. Your Carnot engine, we have actually learned that this is the most efficient. Oh, come on, there's a delay. The most efficient engine, right? So remember what we did was to look at this kind of couple engine between. So here's a Carnot engine. Do this properly. Carnot engine. So see, not having. Okay, now man. So here we have what was it before? It was an irreversible engine. And for Carnot engine, you get Carnot engine from Carnot processes, which you allow reversibility here. So one could actually reverse the order here. So you have theta 1 here, theta 2 with the temperature. So this will be Q1, Q2. So you can do work on this system to transfer. This is a colder body. So theta 2 is less than theta 1. So what do? We reverse it. Okay. Usually a hotter body goes into the colder body, the heat. Okay. But one can reverse this provided we do some work over here. And here would be taking say Q1 dash out of this hotter bath, okay, or surroundings to the colder bath. Okay. So we have learned those, and since Carnot engine is the most efficient, we also know this. This is R means reversible here. So the efficiency of the reversible engine, which is the Carnot engine, is always greater than the irreversible engine. Okay. Now I'm using the convention where heat taken out from what you call. So if you remember, there are two different conventions. Either I put a negative sign here, or I don't put a negative sign, then I assume it's to be in this particular context. So if I put a negative sign to show that it's a heat drawn away from the system, then this equation over here about efficiency becomes this minus Q2. This is Carnot engine, so this is this one. So this one is already reversed, so you have to think the right way around first. Q2 is released from the Carnot engine into the bath below, and Q1 is taken from the heat bath above. So that is the efficiency of the Carnot engine, and this has to be greater than 1 minus, in this case here is your Q2 dash, okay, which comes from your irreversible engine, and then this will be Q1 dash. Okay. But you also know this, that in the case of your Carnot engine, you can always get this idea of ratios of heat to be related to your temperature scale, the absolute temperature scale. So this is from another part of the lectures before. The ones before, this one doesn't have the negative sign, but now I can put in the negative sign just to indicate that heat is drawn from there. So I have that. Invite someone? No. I want to go up. Yeah. Okay. So what we want from here, from this thing, we want to apply it to here, and then you'll see that by some amount of rearranging, then I can actually show that this Q2 dash divided by Q1 dash has to be greater than T2 or T1. Let me just check. I'm just afraid of being disconnected. Okay. Okay. So what do we do after that was to consider the case of the infinitesimal heat changes. oops, the other way around. So consider small heat changes. So in this particular case, we would like to see the case of, say, dq1 dash and dq2 dash in irreversible engine. Okay. So in this particular case, what if one uses that, okay, so instead of the finite amount here, I'm going to consider the small heat changes, then I should be able to rewrite this in terms of this dq1 dash over t1, oops, too close, over t1 plus dq, running out of space in my tab. Sorry for the horrible looking Q there, but okay. So divide by T2, and this from that, no, so I'm replacing dq q2 dash by dq2 dash and q1 dash with dq1 dash. So I'll be able to write this as that. Okay. And the small heat changes, one can consider now arbitrary irreversible cycle. And then you can think of, just like before, we have the reversible, finite reversible cycles being summed up from a small, tiny cycles, reversible cycles. You can do the same. Can do the same for the case of the irreversible cycles too. So I can now integrate this. So this is now irreversible over t. This has to be less than 0. Okay, and that almost give you the idea of, okay, in the case of an irreversible cycle, your entropy has to be always increasing, but okay, it's not obvious from here. Let me just do another thing here. Oops. So now you have this for the case of reversible cycle. So let's compute in a cycle. Consider next. A cycle consists of two parts. Consists of one reversible path with another, with one irreversible. So how do we do this? So you remember, these are just like your Carnot cycle before. So instead of all just reversible cycles or reversible processes, I consider here, for example, this is reversible. So this is going from A to B. I should mark what this is. This is P and V here. Okay. and then the other part going back, okay, this will be irreversible. Okay, so so if you move around the two paths, then I'll be able to write down the following. Let me just write down first. This composite path because part of it is actually irreversible. Path is irreversible. Okay, because the lower part is already irreversible. It's only the upper part which is reversible. So in other words, the previous equation that we had, going down, should hold. So this one we should have it to be true for this path. So that means I can now write the following. So this over the reversible case. So this goes from A to B. So this is dq, reversible over t plus going the other way around, which is going from B to A. It's looking horrible now. dq irreversible. Okay, less than 0. So rearranging that, then one should have following, that going from A to B using the irreversible path, T is always less than going from A to B using the reversible. But what is this? This is essentially just your entropy. Okay? So in other words, what we have here, let me just write it down now. Okay, your entropy is a state function. So the state function is only defined through it should be integral over loop for a state function should always be 0. So that only works for the case of the reversible path. How do I get so this would actually implies the following. The one that's related to the state function should be this, because this is coming from reversible path. So this now becomes that. Less than your entropy, because dq over t is essentially your entropy, well, infinitesimal entropy, but now being integrated between B and A and B. So this will now be dependent only on the endpoints. Okay, so this depends on the endpoints only. So finally, you consider the case where B is close to A. So in other words, I can think of B is roughly A plus delta A if I want to. So delta A is quite small. Then I can rewrite this whole thing now as follows. I have only a small change in your heat, okay, over the temperature, and then this will be your small change going from a point A to the neighboring point B, okay, given by that. So you have this infinitesimal case. And this is called Clausius inequality. And we are almost there. Remember that, okay, for thermally isolated system, okay, there cannot be any heat coming in because it's thermally isolated. So Q will have to be equal to 0, or delta Q has to be equal to 0. Okay, because it's thermally isolated. Okay, so in other words, if I include this into the picture, then I would now have 0 less than delta S, or delta S always being positive. In other words, this is what we call the law of increased entropy, which is just a restatement of your second law in the context of the heat engines that we discussed before this, but now converted into this idea of law of increased entropy. Okay? So this is probably much well known to physicists rather than the one with heat engines, because heat engines are using a very archaic or very old language kind of thing. All right, so what are some other notes that one should also take lesson from here? The other thing that one should take lessons from here, okay, first is this thing: any thermally isolated system, entropy is always increased. And then you also know that if thermal isolated system goes to equilibrium, then the final state of that, which the equilibrium state, the final state, the one already achieving equilibrium, should have the maximum entropy. And once you reach the maximum entropy, once maximum entropy is reached, there will be no other changes. Okay. So these are things that one can actually sort of the implications from that law of increased entropy, one could actually derive this conclusion. The other one is probably it also relates to something else, because you know that what happens in equilibrium is that let's suppose you consider a hot body sort of dissipates the heat. So what happens is it can only flow in one particular direction. Okay, so observation also tells us. I'm just worried about getting disconnected. Okay, observation tells us that just read my notes. Observation tells us that heat can only flow from hot body to colder body, and that's what happens in equilibrium. Okay? So the other observation that one also can say is that somehow this is related. Maybe I should write related observation. Okay, your changes are probably no, and your changes are always related to a preferred direction of time. So can we conclude that time is actually related to this second law of thermodynamics? No, we can't. It's not properly known that this is actually true or not, but no, people suspect it has to be related to one another, but no, your thermodynamics does not explain why you have a particular error of time. Okay? So these are things I probably want to stop there because it gets more philosophical from there. So and the rest is going to be some examples. Okay, so I will stop there for today, and I will upload these notes later on once I finish typing them. So are there any questions? I will take the attendance first. Let me just go here, not here, the other one, go here, and download attendance. Okay, are there any questions at this stage? I will try to start giving you a first assignment questions in order for you to prepare for you. So your first test, my estimate should be in the 6th week rather than the 5th week. Okay. Okay, if there are no questions, I should now end the session in some sense. Okay, thank you everyone.
Thank you.